Hi, everyone. I'm Bibit, and on behalf of myself and my collaborators, I'd like to introduce our work towards human haptic gesture interpretation for robotic systems. Physical human-human collaboration is inherently rich in contact between the humans themselves, objects, and the world around them. In this assembly example, the people are continually assessing through touch the other's readiness to move on with tasks like passing objects between each other and sharing the load of a single object as a pair. For this scenario to instead involve one human and one fully articulated robot, the robot needs to interpret these contact events. To accomplish this, the robot needs to convert its raw sensor data into semantic descriptors, allowing higher level planners to operate on an appropriate behavioral task level. It's the goal of this work to build this intermediate gestural interpretation layer, which would enable future robotic research and development on high-level behaviors. To obtain this goal of equipping robots with an informed sense of touch, first, we must focus on the hardware presence of the robot. Next, we will discuss our proposal for broad task-oriented touch gestures before discussing our exploration over feature sets and classification algorithms. We will conclude with results and some discussion of what we found. Starting with the hardware, we chose to use a UR5E robotic arm due to its common usage as an pHRI research platform. Say this robot is in contact with something, an object, a human, or the environment. There's broad literature proposing ways to detect such contact, starting with a variety of custom touch sensors that can go directly between the robot and object. These sensors are often complex and delicate, and there is certainly no standard fingertip touch sensor. Progressively getting further away from the contact site, other options include contact microphones in the robot housing, or even monitoring actuator currents within the robot. This requires knowledge of the kinematic structure and state of the robot and can be difficult to parse when the robot is in motion in particular. Fully external visual sensors require markers not only on the robot, but also on any object or person with which you'd expect the robot to interact. Really, what we want is something common, inexpensive, robust, and generally simple. Our proposal here is to use the built-in wrist force torque sensor that's already incorporated into most of these robotic arms. This is the simplest way to approach the problem, so we aim to explore the boundaries of the capabilities before considering a more complicated sensing arrangement. With that in mind, the next choice for us is to determine the relevant touch gestures for task-oriented pHRI. Starting with the touch dictionary from Yohanan and McLean, we can begin to pare down this list of 30 by first eliminating any weight-bearing movements, recalling that we intend to use a robotic arm typically mounted to a fixed table or otherwise to a heavy mobile base. Second, we eliminate purely emotional movements because our intentions are for the robot-human team to accomplish a task. And lastly, we unify the remaining gestures to incorporate the overall motion, but exclude distinction of what part of the hand is used. The thought here is that our hands easily could be full when working towards a goal. So we want to be able to communicate with our knuckle what we could communicate with our fingertips if our hands are full. What we are left with is 4 categories defined against several other works in the literature. We name each of these categories to unify their in-class similarities while still distinguishing their differences. Here, taps involve impulse-like impacts, whereas touches sustain impact from one direction for a longer duration of time. Grabs involve sustained contact from more than one direction, whereas slips involve contact that is sustained with some dynamic friction between the two interacting bodies. All of these definitions otherwise are impartial to the direction of application, gesture magnitude, or part of the human hand that is used. With these in mind, we collected a data set involving 2 users, 1 male, 1 female, and 2 robot configurations with and without an installed claw and effector, totaling in 24 minutes of 500 Hertz force sensor data. This data set looks like a time series of 3 force channel readings, which we labeled by hand by first identifying the beginning and end of each gesture within the time series. Then we grabbed 600 millisecond windows of this time series, generated every 100 milliseconds, providing each of these snippets with a label of any ongoing or transitioning gesture type or lack thereof. These snippets look like this, with the corresponding labels demonstrated here at the top. In total, we have a balanced training set of nearly 1,600 gesture examples, validation set over 200, and balanced test set over 100. Next, we can consider what information our system uses to discern between these gesture types. The simplest option is to use the full snippet's worth of force data directly. However, this isn't often feasible with certain classifiers due to its high dimensionality. One alternative to this is to manually construct a feature set, which we did taking inspiration from some audio signal processing techniques. And we also tried 2 common compression techniques, principal and independent component analysis separately. The second approach is to learn a lower dimensional representation, typically through the bottleneck of an autoencoder model. We constructed 2 such autoencoder architectures and obtained 2 different feature sets to try, bringing our total of explored feature sets to these 6. Next, considering classifiers, we pursued 3 common ones: decision tree, SVM, and neural network, specifically a temporal convolutional neural network. We note that the neural network is really the only reasonable algorithm capable of working with the full force data feature set. And furthermore, it's capable of determining its own lower dimensional features. So we only combine the neural network with the full force data, which is also not tested with either of the other algorithms. For each of these, we performed hyperparameter searches for these combined with each of the feature sets. And this search was necessary for increasing performance significantly, as the performance of random combinations here yielded mostly low validation accuracies, exemplified here for the neural network search in particular. Let's look at the performance. Here are the overall accuracies on the balanced test set. We note that all of them performed significantly better than the 1 in 5 chance of a correct guess. And the best performance overall was by the neural network on the raw force data. The best performances within the other algorithm types were on the ICA version of the manual feature set for decision tree, and the larger of the autoencoder bottleneck features for SVM. We can break these percentages down a little to see more granularity in their performances, noting that certain classes like touch aren't guessed as often overall, and other classes like grab are often falsely guessed. Let's take a closer look at how these models work in action. So we start with the physical interaction in the top left and the corresponding snippet and ground truth label below. Now I introduce predictions from each of the 11 trained models, remembering that these vary in algorithm as well as in feature set. Let's take a closer look now at the top performer, which is the neural network. A TSNE plot of a convolutional layer for the validation set indicates clustering of gesture types. The touch gesture in particular has several fragmented clusters, indicated that it often conflates touch snippets for some of the other classes, specifically slip in the lower right area of that graph. Zooming back out to remind ourselves of the best performers of each algorithm type, let's take a closer look at these 3 models in particular through analysis of some confusion matrices. Let's start with the decision tree. An interesting part about this confusion matrix is it indicates that this model almost entirely forgot the touch gesture exists, possibly resulting in overinflating its performance in the other categories since it guessed those more often. Comparing this to the best SVM and neural network, we see those have more evenly spread predictions across classes, not having this strong bias towards or away from certain classes. The neural network confusion matrix shows touch snippets often confuses slips, as expected from looking at the TSNE plot earlier. A noted commonality between the SVM and neural network performances is that they both missed a high number of TAP snippets, which was surprising because TAPs had some of the highest recall in the training and validation sets. Further inspection revealed that the test set had some particularly small amplitude TAPs, a problem which a larger data set might possibly accommodate for. Interestingly, the best decision tree didn't have this problem at all, perhaps because its feature set was derived from our manual feature set, which had a template correlation matching feature specifically designed to pick out TAPs. Hopefully for us, we can compare our findings with numbers from Jung et al., who provided a large confusion matrix among their 14 proposed gesture types. Rearranging and combining their data into our gesture definitions, we recover that they obtain an 81.5% test set accuracy against our definitions. Doing a deeper comparison between our methods highlights why this is important. Jung et al. Defined 14 gestures captured in a large data set collected by a large pressure sensor array. They manually calculated 54 hand-designed features and tried 4 different algorithm types before identifying the best performance with SVM. Against our 4 gestures, this accuracy is 81.5%. In contrast, our dataset was a quarter of the size, collected by a generic force torque sensor already integrated off the shelf into our robot. We swept over both feature set and algorithm type to ultimately match Jung et al.'s performance with a neural network on the raw sensor data. First, this shows that the extra effort of designing and computing manual features is unnecessary. Second, forcing ourselves to stick with the manual feature set, our best accuracy would have been in the 60s. Adding in this extra exploration unlocked higher performance that compensated for a much smaller data set. Lastly, with smaller scope of gesture types, their use of a complex sensor array provided no advantage over our use of a single force torque sensor. To conclude with some avenues for future work, first, we discovered opportunity for us to combine approaches to improve overall predictions, mainly noting from our confusion matrices that some derivative of our manual feature set might help our neural network catch more TAP snippets. Second, all of our gesture definitions were human initiated, and there could be an enormity of information for a robot to gain if this directionality went both ways. Lastly, we hope to demonstrate new capabilities enabled by our developments through a collaborative physical HRI task. With that, I thank everyone for your time.